I'd like to give you an overview, a partial overview of the work we have been doing the past 15 months. So this is the whole team, you see, Tryphon Georgiou and Yonxin Chen. Basically, it works like this. You see, there are two elderly people leaning on the young person. You know, that's really symbolic of our collaboration. Yes. And I'm going to talk, I was lucky that Christian gave this talk before, beautiful talk. And so let me start with something you're all very familiar, the fluid dynamic version of optimal mass transport due to Benamont and Brenier, in the case of a quadratic cost function. And we have this variational problem, and basically we have the solution is through a solution which is typically not a non-classical solution of a Hamilton-Jacobi equation, but we have to satisfy the second boundary condition. Okay, so we need this solution to have a boundary condition psi1 so that indeed, when you use gradient psi as the velocity, the continuity equation will wind up in the desired density. Of course, I'm assuming that I have absolutely continuous marginals. What about Schrödinger problem? You already heard a lot, so I can be rather sketchy here. You know, you have this large number of Brownian particles, and you have two empirical distributions. Somehow they don't match. He was thinking of Brownian particles, so the transition density is the one displayed. So the particles have been transported in an unlikely way. Still, he poses the question of the many unlikely way in which they have been transported. Which one is the most likely? It's quite impressive. This question is posed clearly in 1931. The mathematics to even understand this question came several decades afterwards. All right? We don't even have the notion of a stochastic process. We don't even have the notion of a probability space. But Schrödinger, as he was at it, he had a couple of free minutes, not only formulates the problem, to a large extent, he solves the problem. Okay, and Christian was hinting how he did it. Of course, he had, this is the Austrian school, Boltzmann, discretize, and the Stirling approximation. That's how you do it. And Lagrange multipliers. So it's a beautiful piece of science considering particular times. Of course, the motivation is even more beautiful. You know that Schrödinger never accepted the orthodox theory of quantum mechanics, so he was trying to find a more classical version of quantum mechanics based on diffusion processes, and he had noticed that here there is a remarkable reversibility. In what? In this problem. So the solution, called Schrödinger bridge, justly so, has this property that if you swap the two marginals, the solution is simply the time reversal of the previous. Now, to really appreciate this, you should consider the diffusion processes that had been introduced and studied by theoretical physicists for basically since 1905, Einstein, Smoluchowski, Fokker, Planck, and so on, to model irreversible phenomena. So even this is incredibly remarkable, 1931. Shortly afterwards, there's a paper by Kolmogorov with a similar title. He also understands that diffusion process can be used to model reversible phenomena. It took up to Nelson 30 years later to have a version of quantum mechanics based on diffusion process. But this, I don't want to branch out too much. The bottleneck of the whole thing is this Schrödinger system, which is on the slide, okay. In 1988, you see how much later, Fermat finally goes back to Schrödinger's original motivation. He says, look, this is a problem of large deviation of the empirical distribution. In the meantime, Sanov's theorem had been established. So it is a maximum entropy problem on path space. So Schrödinger was formulating and to some extent solving such an abstract abstract problem in 1931. So the bottleneck is a real bottleneck. This is very hard to actually establish existence and uniqueness. Schrödinger says, I think there should be existence and uniqueness because the problem is so natural, unless the marginals are really nasty, something like that. Anyway, here are the names of the people that have mostly contributed. See, it's very discontinuous interest, but by first-class people. Anyway, and Christian also recently extended a little bit this. So what is the maximum entropy formulation? It is over there. You minimize relative entropy, but these are measures on path space, on continuous trajectories, okay, which have the prescribed marginals. This is what that symbol means, D of rho 0, rho 1, okay, and say they are equivalent to stationary Wiener measure. This is what you get if you give Lebesgue measure as initial measure to the Wiener process. So you get, of course, not a probability measure, in fact, not a finite measure. But it's a useful technical tool. And then you can use Girzanov, okay? And then, thanks also to the results of Jamison, you can turn this into a stochastic control problem. And this was noticed by a number of people around late 80s, early 90s, okay? And what does the control problem look like? It's a stochastic control problem that I don't have the time to show you because I'm going to go immediately to the fluid dynamic counterpart. Why am I doing this? Well, we started with Benamou-Brenier. This is exactly the ground on which these two problems meet more naturally and in fact can be generalized. So we're going to look at a fluid dynamic Eulerian, if you like, version of this problem. It's over there on the board. The prior is Wiener measure, stationary Wiener measure, but with variance epsilon, exactly like Christian had before, right? He had 1 over k, if you remember. So this is what the problem looks like. Now you look at this and you remember Benamou-Brenier. What is the difference? You only have a Laplacian. It looks very much like a regularization. And in fact, a number of beautiful results showed this. But I cannot resist telling you that there is another fluid dynamic representation of the Schrödinger bridge problem. And this one is also quite interesting. You see, now the equation is the same. It's a continuity equation, right? Or Liouville equation, whatever you want to call it. The criterion is different, all right? And the Schrödinger bridge is the minimizer of this problem. Why is this interesting? Well, it's interesting because we know that displacement interpolation gives me a geodesic in Wasserstein space, all right? So it solves this problem without that, all right? But this has also a clear significance. This is like a Fisher information functional, okay? So obviously the entropic interpolation, which is connected to, which is given, comes with the Schrödinger bridge, cannot be a geodesic, right? But it minimizes another action function that has an extra term, which is just a Fisher information. There is a version of this with non-trivial prior. We're doing all of this with the prior, which is Wiener measure, which is like a uniform measure on path space, if we want to say it. What if it is a general Markovian measure? Schrödinger bridges have been extended to a general Markov measure, even with creation, killing, Markov diffusion processes. Well, there is a generalization of this formula, and you will get a relative Fisher information functional. Okay, so this is all quite interesting in the direction of the geometry. Okay, I don't have time to go into that now. So everything that we have seen hints that we can use the Schrödinger bridge solution as an approximation to optimal mass transport, and there are a number of results and people that have contributed over there. In particular, Christian also wrote, besides his contribution, he wrote a beautiful survey paper, which was very inspiring for us. And so now that we realize this, we say, can we actually compute the solution to optimum mass transport using the Schrödinger bridge? Well, there are a number of problems with this. The solution to the control formulation of the Schrödinger bridge problem is typically not given in an implementable form. Okay, existence and uniqueness for the Schrödinger bridge, excepting Forte paper, which is based on an iteration, is given, in a non-algorithmic way, not computable way. Then most of the theory, at least the theory that I know of the Schrödinger bridge problem, is for non-degenerate diffusion. Okay, but there are important applications. Think of the Osten-Uhlenbeck model where you have degenerate diffusions. And where noise and control enters through the same channel, engineers are not happy with that. This excludes a lot of engineering models. No steady state theory. What about if the final marginal is at plus infinity? I want to go asymptotically to a distribution. This no is a bit of exaggeration, I will say. There is piecemeal work here and there, but really very little. And finally, what about optimum mass transport with a non-trivial prior? The Schrödinger bridge problem can have any Markovian prior. What about the optimal mass transport? You know, we know by the convergence that basically it corresponds to the situation when the prior is this uniform with vanishing variance. What if it is a general prior? So we try to partially remedy to this situation. And what do you start with? Well, if you come from control theory, you start with the simplest but also most important model for engineering, economic applications, so on. You start from the Gauss-Markov processes, okay? So you start from that. You want to find a control which has minimum energy, all right, for this model, and we'll start from, everything is linear here, so we are in a Gaussian world. We start with a Gaussian distribution. We want to wind up to a Gaussian distribution. You can set the mean equal to 0 because it's very easy to take care of that. Okay, so basically you're going from one covariance to another covariance. Okay, there are a number of applications, also some very modern in engineering, where actually the task is precisely to drive a density to a density rather than, you know, going from one point to another point, which is a very classical problem in optimal control. All right, what you can show is that if you have what is called controllability, if these A, B are constant, this is a geometric condition amounts to this matrix having full row rank. You can show that the problem is always feasible. At least you have one control that will do the task. Okay, but this result is highly non-trivial because you see the control may be handicapped with respect to the noise. The noise, say, may affect position, and your control might be able to affect only, you know, a derivative or something. So but still, under controllability, you can show that you can actually transfer. And we consider these two problems. So the first, well, the first problem is already here, of course, okay? In finite time, you want to drive with minimum energy your system to the final Gaussian. But there is also the asymptotic problem, okay? So now we take a constant feedback control. We want to minimize power, and in such a way that the resulting equation will have this as invariant density, okay? And you can show that this problem does not always have a solution, okay? Not all values of sigma can maintain, okay? Now here I'm mentioning some previous contributions. There is really scattered work, which is also sometimes difficult to connect to this problem because it comes under different, it is disguised, like the skeleton work. Brockett recently, I don't know if you're familiar with control theory. Brockett is one of the main figures in the control world. And then there is some more recent work. Often the assumption under which they have studied similar problems are not natural, like having a non-singular diffusion coefficient, which would amount to B1 transport being positive definite. This again would rule out a lot of interesting applications. So what do we have? Well, we got some sufficient conditions. The sufficient condition for the finite horizon case are in terms of two matrix Riccati equations. Okay, you see we have the nonlinear coupling at the boundary, which is typical of the Schrödinger system. But then we have also dynamical coupling if the two channels of the noise and the control are different. Now this is interesting because this basically is outside of the classical Schrödinger bridge theory. There is no maximum entropy problem. The two measures are mutually singular. You see, because we have a degenerate diffusion and we have that control and noise enter through different channels. The Rado-Nikodym derivative does not exist. So which means what? It means that once you have transformed the Schrödinger bridge problem into a control problem, you can consider more general problems that not necessarily have the original large deviation motivation. This makes perfect sense. Okay, so you have this sufficient condition. We have no idea about existence, uniqueness, or how you integration is also looks very challenging. In the asymptotic case, which is of course of major importance in engineering applications, we get an algebraic condition. Okay, so this is in these two papers that will appear in the transaction automatic control. Another area of application, natural area of application, is of course statistical physics, where states are probability distributions, right? So we think about driving a system to a probability distribution. This is most natural for statistical physics models, for instance, stochastic oscillators. So we consider in this paper that will appear shortly, again, the asymptotic steering to a desired steady state. For instance, cooling is a very nice area of application. Cooling means you try to drive the system to a steady state which corresponds to a lower effective temperature, reducing the effect of the bath on your system. There are all kinds of applications, okay? Surface topography, resonators, micro and macro resonators, and so on. So this is a whole area, and also you can pose the problem in finite time, right? Okay. And in both cases, here of course we have the stochastic oscillator, so we have a degenerate diffusion and so on, but it's a good degenerate diffusion because it's hypoelliptic, so you can do it. What about, I mentioned that there seemed to be no optimum mass transport with prior, but it makes a lot of sense to me. Suppose you have set up your transportation problem, your transportation in an optimal way, and then someone comes and tells you, look, the initial distribution of the goods is not really what you thought it was, or the final is different, or both. What do? You still want to keep close to the transportation plan you have already organized, no matter what you're using, right? So this is a natural problem to consider. I want to minimize now, you see, the square of the difference between my VP, that was the solution of the original problem, okay, with a new V, subject to that, but with the actual marginal densities that I have observed now. And you can easily generalize the variation analysis here. Is this really new? Well, no, it's not really new because, of course, you know, optimal transport has studied problems where the cost function comes from an action like that. If your action has the form x dot minus vp, okay, you see that we recover exactly what we had before, the optimal mass transport with prior. So why do we do this? Well, there are two reasons. First of all, conceptually, it's very nice to have this optimal mass transfer with prior to compare to the Schrödinger bridge with general prior. Secondly, we're interested in situations where actually we're going to have, you know, a problem like this. If you want to put it in that way, you can. You would have an x dot minus vp, but then you would have a b, what is it? bb prime pseudo inverse. B is not even square, which means that this problem is not strictly convex with respect to x dot, which is a crucial assumption, of course, in the calculus of variation and in the classical optimal mass transport. So existence and uniqueness of the transportation has to be proven independently. We have succeeded in the linear situation, okay? There is you can use some control result, change the coordinate, and bring it back to a classical problem. So, all right, here I don't need to say this because Christian has already said it, okay? How the convergence occurs and so on and so on. And these are two papers that deal with this, where you can find what I just mentioned. Let me just give you one example. For instance, Smoluchowski model for a planar Brownian motion, okay? We know it's a good model in an overdamped situation, so we have a quadratic potential, so everything will be linear. We are in a Gaussian world. Suppose we only want to shift the mean, okay? We keep the same covariance. We only want to shift the mean. So what I'm going to show you, you will see a tube, a transparent tube, which represents the 3 sigma region, okay? Okay, this is the interpolation. The entropic interpolation will have some trajectories of the Schrödinger bridge, and I have epsilon equal to 9. Let's reduce the effect of the noise. You see the tube is getting, it shrinks down, epsilon equal to 4. If you take epsilon really small, you get smooth trajectories. What about the trajectories of optimal mass transport with prior? You see they're exactly the same. So this is with prior. Without prior, there would be straight lines, right? The trajectories of, yes? Okay, so this shows this convergence that Christian was talking about in a slightly more general situation when you have a non-trivial prior. All right? Okay, it's a long story. I don't have the time. In general, there is a geometry here. Let me just mention this. It's curious that people have not noticed phi and phi hat of the Schrödinger system are unique up to multiplication of one by a positive constant and division of the other by the same constant. So the convergence cannot be to a function. It has to be to a ray. But of course, then you need projective geometry. You need the right geometry. And the right geometry is given by the Hilbert metric. And there are beautiful results by Garrett, Birkhoff, and Bushell that they will give you that these maps on cones, okay, under suitable assumption, contract the Hilbert metric. It's curious that it had not been noticed. So using this, we have been able to prove things, but also to get algorithms. We have iterative algorithms to compute solution of the Schrödinger bridge, at least for, you know, Markov chains or quantum channels and so on. One final thing here. Once you have this powerful computational approach, you can start doing applications. For instance, you want to interpolate these two images, okay, MRI, all right? Okay, you take very low noise and you get this. Of course, if you increase the noise, you get blurred pictures. Okay, I'll stop.